Tonight, we're going to talk about the true size of the universe. Not the version you've imagined, not the scale you've been taught. The actual, measured, verified size of everything that exists. We're talking about distances so vast that light itself takes billions of years to cross them. Structures so large that our entire galaxy becomes a speck of dust. Numbers so extreme, they stop having any meaning. And by the end of tonight, you're going to understand why even the biggest numbers you've heard don't come close to capturing how vast the universe really is. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Most people think they understand how big the universe is. They've seen the pictures. Earth floating in space, tiny and blue against the darkness. The solar system, with its 8 planets, spread out around the sun, the Milky Way, a spiral of hundreds of billions of stars. Maybe they've even heard about galaxy clusters or the observable universe. And they think, okay, space is big, really big, incomprehensibly big. But here's what they don't realize. Every single one of those mental images, every comparison they've heard, every attempt to explain cosmic scale, all of it underestimates the true size by factors so large that the numbers become meaningless. The universe isn't just bigger than you think. It's bigger in ways that break our ability to comprehend bigness itself. Let me start with something familiar. Earth. You live on it. You know roughly what size it is. About 7,917 miles in diameter. Big enough that you could spend your entire life exploring it and never see everything. There are mountains you'll never climb, oceans you'll never cross, cities you'll never visit. From a human perspective, Earth is enormous. But let's put that in context. The Moon, Earth's only natural satellite, is about 2,159 miles across. That's roughly 1/4 the diameter of Earth. If you place them side by side, you could fit about 4 moons across Earth's diameter. The Moon seems huge when you look up at night, but it's actually quite small compared to Earth. The distance between Earth and the Moon averages about 238,855 miles. The Apollo astronauts who traveled to the Moon in the late 1960s and early 1970s took about 3 days to make the journey. That's the closest celestial body to Earth, and it's already farther than any human has traveled since 1972. Now, let's move outward to the Sun. The Sun is about 864,948 miles in diameter. You could line up 109 Earths across the Sun's diameter. But diameter doesn't capture the real difference. Volume matters more. The Sun's volume is so large that you could fit about 1,300,000 Earths inside it. The distance from Earth to the Sun is about 92,957,102 miles. This distance is called 1 astronomical unit. It's the baseline measurement we use for distances within the solar system. Light, traveling at about 186,282 miles per second, takes 8 minutes and 20 seconds to reach Earth from the Sun. When you look at the Sun, you're seeing it as it was 8 minutes ago. If the Sun suddenly vanished, we wouldn't know for 8 minutes. Let's keep going outward. Mercury orbits at about 0.39 astronomical units from the Sun. Venus at about 0.72. Earth at 1. By definition. Mars at about 1.52. Then we hit the asteroid belt. a region of rocky debris between Mars and Jupiter. Jupiter, the largest planet in our solar system, orbits at about 5.2 astronomical units. Saturn at 9.5, Uranus at 19.2, Neptune at 30. Neptune is the farthest planet from the Sun. Its orbit takes it about 2,795,000,000 miles from the Sun. Light from the Sun takes about 4 hours to reach Neptune. But Neptune isn't the edge of the solar system, not even close. Beyond Neptune lies the Kuiper Belt, a region of icy bodies, including Pluto and thousands of other dwarf planets and comets. The Kuiper Belt extends from about 30 astronomical units to roughly 50. Beyond that is the scattered disk, where objects have highly elliptical orbits, some reaching 100 astronomical units or more from the Sun. And beyond that, far beyond that, is the Oort cloud. The Oort cloud is a theoretical shell of icy objects surrounding the solar system. We've never directly observed it because the objects are too small and too far away to see with current telescopes. But we know it's there because of the comets that occasionally fall inward toward the Sun. Long-period comets, the ones that take thousands or millions of years to orbit, come from the Oort cloud. The Oort cloud is thought to extend from about 2,000 astronomical units to as far as 100,000 astronomical units from the Sun. 100,000 astronomical units. That's about 1.6 light years. A light year is the distance light travels in 1 year at 186,000 miles per second. The Oort cloud extends to about 9.4 trillion miles from the Sun. The Oort cloud marks the true edge of the Sun's gravitational influence. Beyond it, you're in interstellar space, the space between stars. The nearest star to our Sun is Proxima Centauri, about 4.24 light-years away. 4.24 light-years. That's about 25 trillion miles. If you could somehow travel at the speed of a commercial airliner, about 560 miles per hour, the journey to Proxima Centauri would take about 5 million years. 5 million years of continuous flight. The fastest spacecraft humans have ever built is the Parker Solar Probe, which reached speeds of about 119,000 miles per second during its close approaches to the Sun. At that speed, it would still take about 6,700 years to reach Proxima Centauri. Voyager 1, launched in 1977 and still traveling through space, is moving at about 10.6 miles per second relative to the Sun. At that speed, it would take about 75,000 years to reach Proxima Centauri, if Voyager 1 were headed in that direction, which it's not. If the Sun were the size of a basketball sitting in New York City, Proxima Centauri would be another basketball sitting in Los Angeles. Everything in between, the 3,000 miles of the United States, would be almost completely empty. Maybe a few grains of dust scattered here and there, representing the occasional comet or asteroid, but mostly nothing. That's interstellar space. Vast beyond comprehension, with occasional points of light separated by unimaginable distances. And Proxima Centauri is the nearest star. The second nearest star system is Barnard's star, about 6 light-years away. Then Wolf, 359, at about 7.8 light-years. Sirius, the brightest star in Earth's night sky, is 8.6 light-years away. These are our neighbors, the closest stars to the Sun. And they're all separated by distances that would take tens of thousands of years to cross with current technology. Proxima Centauri is a small red dwarf star, much dimmer than the Sun. It has about 12% the mass of the Sun and about 14% of its diameter. If you replace the Sun with Proxima Centauri, Earth would be plunged into near darkness. Proxima Centauri emits only about 0.17% as much light as the Sun. It's so dim that even though it's the closest star to Earth, you can't see it without a telescope. It has an apparent magnitude of about 11, far too faint for the naked eye. Proxima Centauri is part of a triple star system called Alpha Centauri. The other two stars, Alpha Centauri A and Alpha Centauri B, are slightly farther away at about 4.37 light-years. Alpha Centauri A is similar to the Sun in size and temperature. It's actually slightly larger and hotter, with about 1.1 times the Sun's mass and about 1.5 times its luminosity. Alpha Centauri B is slightly smaller and cooler, with about 0.9 times the Sun's mass and about 0.5 times its luminosity. Alpha Centauri A and B orbit each other in an elliptical orbit that brings them as close as 11 astronomical units and takes them as far as 36 astronomical units apart. One complete orbit takes about 80 years. Proxima Centauri orbits both of them at a much greater distance, perhaps 15,000 astronomical units away, taking about 550,000 years to complete one orbit. This distance is so large that some astronomers have questioned whether Proxima is truly gravitationally bound to the other two stars or just passing through. But recent measurements suggest it is indeed part of the system. In 2016, astronomers discovered a planet orbiting Proxima Centauri called Proxima Centauri b. The discovery was made using the radial velocity method, watching for tiny wobbles in the star's motion caused by the gravitational tug of an orbiting planet. Proxima Centauri b is roughly Earth-sized, with a minimum mass of about 1.27 Earth masses. It orbits in the star's habitable zone, the region where temperatures might allow liquid water to exist on the surface. The planet orbits very close to its star, about 0.0486 astronomical units, closer than Mercury orbits the Sun. But because Proxima Centauri is so dim and cool, this close orbit places the planet in the habitable zone where temperatures could be similar to Earth's. The orbital period is only 11.2 days. A year on Proxima Centauri b lasts just 11 days. In 2019, astronomers announced the possible detection of a second planet, Proxima Centauri c, orbiting farther out at about 1.5 astronomical units, with an orbital period of about 5.2 years. This planet, if confirmed, would be much colder and likely not habitable. Then, in 2020, they found evidence for a third planet, Proxima Centauri d, even smaller than Proxima b, orbiting very close to the star with a period of just 5 days. Proxima Centauri b is the closest known exoplanet to Earth, and it's 4.24 light-years away. With current technology, a spacecraft would take tens of thousands of years to reach it. The fastest spacecraft humans have built, the Parker Solar Probe, would take about 6,700 years. A human lifetime is perhaps 80 years. 6,700 years is about 84 human lifetimes. That's the distance to the nearest potentially habitable world beyond our solar system. And yet, in cosmic terms, 4.24 light-years is nothing. It's our next-door neighbor. A stone's throw, in galactic terms. Our Sun is just one star among hundreds of billions in the Milky Way galaxy. The Milky Way is a spiral galaxy, meaning it has a central bulge surrounded by spiral arms that rotate around the center. The galaxy is about 100,000 light-years in diameter. 100,000 light-years. If you started at one edge and traveled at the speed of light, it would take 100,000 years to reach the other edge. The thickness varies depending on where you measure. The central bulge is about 10,000 light-years thick. The disk where the spiral arms are located is much thinner, only about 1,000 light-years thick in most places. The Sun is located about 26,000 light-years from the galactic center. We're in a relatively quiet region between two major spiral arms, a spot sometimes called the Orion's Spur or the local arm. The Milky Way has four major spiral arms: the Perseus arm, the Scutum Centaurus arm, the Norma arm, and the Sagittarius arm. Our local spur is a minor arm between the Perseus and Sagittarius arms. These spiral arms aren't fixed structures like the arms of a pinwheel. They're density waves, regions where stars and gas are more concentrated. Stars move in and out of the spiral arms as they orbit the galactic center. When stars enter a spiral arm, they slow down slightly due to the increased gravitational pull. This causes traffic jams of stars and gas, which is why the arms appear brighter. The increased density also triggers star formation. When gas clouds collide in the spiral arms, they can collapse and form new stars. This is why spiral arms are dotted with bright blue regions, areas of active star formation where hot young stars have recently been born. This location is important. If we were closer to the galactic center, the density of stars would be much higher. Neighboring stars would be closer together. In the central bulge, stars are separated by only about 1 light-year, on average, compared to about 4 light-years in our neighborhood. If Earth were located in the galactic bulge, the night sky would be spectacular. Instead of seeing a few thousand stars with the naked eye, you might see tens of thousands. Some stars would be close enough to see as small disks rather than points of light. There would be no real darkness at night. The combined light of so many nearby stars would create a permanent twilight. But that location would also be dangerous. Supernovae would be more common. Radiation levels would be higher. The gravitational interactions between closely packed stars would perturb planetary orbits, potentially ejecting planets from their systems or sending them crashing into their stars. Life, as we know it, might not be possible. Our position in the galactic suburbs, far from the chaos of the center, but not so far out that heavy elements are scarce, is one of the factors that made Earth's development possible. The Milky Way rotates. The Sun orbits the galactic center at a speed of about 137 miles per second. That's about 136,790 miles per hour. At this speed, it takes about 225 million years for the Sun to complete one orbit. This period is called a galactic year. Since the Sun formed about 4.6 billion years ago, it has completed roughly 20 galactic orbits, 20 trips around the galaxy. The last time the Sun was in its current position relative to the galactic center, about 225 million years ago, Earth was in the Triassic period. Dinosaurs were just beginning to evolve. The first small dinosaurs appeared around 230 million years ago. Mammals existed, but only as small shrew-like creatures. The supercontinent Pangaea was starting to break apart. Life existed mostly in the oceans. Land plants were relatively new. That was 1 galactic year ago. Before that, 450 million years ago, 2 galactic years ago, Earth was in the Ordovician period. Life was almost entirely aquatic. Fish were just beginning to evolve. There were no land plants yet, no land animals, just barren rock under an alien sky. 3 galactic years ago, about 675 million years ago, Earth was in the cryogenian period. The planet had just emerged from a global glaciation event called Snowball Earth, when the entire planet may have been covered in ice. Complex multicellular life was just beginning to evolve. 4 galactic years ago, 900 million years ago, life on Earth consisted mostly of single-celled organisms. Some simple multicellular life existed, but nothing complex. No animals, no plants, just bacteria and simple eukaryotes. The Sun has been around the galaxy 20 times since it formed, and each orbit takes 225 million years. Think about that timescale. At the center of the Milky Way, buried beneath layers of dust and gas, is a supermassive black hole called Sagittarius A. Sagittarius A contains about 4 million times the mass of the Sun compressed into a region smaller than Mercury's orbit. To be specific, the event horizon, the point of no return around a black hole, is about 17 times the diameter of the Sun. That's about 14,900,000 miles across. Sounds big, but Mercury orbits the Sun at about 36 million miles. The black hole at the center of our galaxy, containing 4 million solar masses, has an event horizon smaller than Mercury's orbit around the Sun. That's how dense black holes are. Its gravitational pull is so intense that stars near it move at thousands of miles per second. Astronomers have been tracking these stars for decades, watching them complete their orbits around the invisible black hole. The closest stars to Sagittarius A are called S-stars, named S1, S2, S14, and so on. S2 is one of the best studied. It orbits Sagittarius A every 16 years in a highly elliptical orbit. At its farthest point, it's about 1,000 astronomical units from the black hole. At its closest approach, it gets within 17 light hours. 17 light hours is about 120 astronomical units. Still farther than Pluto orbits the Sun, but incredibly close for something orbiting a supermassive black hole. At closest approach, S2 reaches speeds of about 3,100 miles per second. That's nearly 2% the speed of light. About 7,200 times faster than a commercial airliner. Fast enough to cross the entire United States in about half a second. And it's a star doing this, not a tiny spacecraft. A star with perhaps 15 times the mass of the Sun, swinging around the black hole at relativistic speeds. By tracking the orbit of S2 and other S-stars, astronomers have been able to measure the mass of Sagittarius A with high precision. They've also been able to test Einstein's theory of general relativity in the strong gravitational field near the black hole. In 2018, S2 made its closest approach to Sagittarius A. Astronomers watched carefully, measuring the star's position and velocity with unprecedented precision. They observed the star's light being redshifted by the black hole's gravity, exactly as general relativity predicts. They measured the precession of the orbit, the way the ellipse slowly rotates over time, also matching Einstein's predictions. These observations confirmed that general relativity works even in the extreme conditions near a supermassive black hole. Other stars orbit even closer. S62 has an orbital period of only 9.9 years. S4.711 has a period of about 12 years. These stars are moving at incredible speeds, tracing out elongated orbits around the invisible monster at the galaxy's heart. The black hole itself is invisible because nothing, not even light, can escape its gravity once it crosses the event horizon. But we can see the effect. We can see stars being flung around it. We can see gas and dust spiraling inward, heating up and emitting radiation before disappearing forever. We can see radio waves and X-rays coming from the region around the black hole, emitted by matter being torn apart just outside the event horizon. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow. The Event Horizon Telescope isn't a single telescope. It's a network of radio telescopes spread across the Earth, working together to create an Earth-sized virtual telescope. By combining observations from telescopes in Hawaii, Arizona, Chile, Mexico, Spain, and Antarctica, astronomers created an image with a resolution sharp enough to see the shadow of a black hole. The first image wasn't Sagittarius A. It was the supermassive black hole at the center of the galaxy, Messier 87, about 55 million light-years away. That black hole is about 6.5 billion times the mass of the Sun, much larger than Sagittarius A. Its event horizon is about 24,800 million miles across, about 7 times the size of Neptune's orbit. The image shows a ring of glowing gas surrounding a dark, circular region. The dark region is the black hole's shadow, the area where the black hole's gravity is so strong that light curves back on itself. The ring is gas spiraling into the black hole, heated to billions of degrees and emitting radiation before it crosses the event horizon. In 2022, the Event Horizon Telescope collaboration released an image of Sagittarius A as well. The imaging was more difficult because Sagittarius A is smaller and the gas around it moves faster, creating a more variable target. But the team succeeded. The image shows the same structure: a bright ring of gas surrounding a dark shadow. This is what the black hole at the center of our galaxy looks like. Or rather, it's what the region around it looks like, since the black hole itself is invisible. The ring is about 52 microarcseconds across, as seen from Earth. A microarcsecond is 1/millionth of an arcsecond. Remember, an arcsecond is 1/3000/600th of a degree. 52 microarcseconds is phenomenally small. It's the apparent size of a tennis ball on the Moon, as seen from Earth. And astronomers imaged it. By working together, by combining data from telescopes around the world, by developing sophisticated algorithms to process the data, they created an image of an object 52 microarcseconds across, located 26,000 light-years away. That's extraordinary. The Milky Way contains somewhere between 100 billion and 400 billion stars. The exact number is hard to determine because many stars are hidden behind dust and we can't see the entire galaxy from our position within it. The best current estimate is around 250 billion stars. 250 billion. If you tried to count them at a rate of 1 per second, never stopping to eat or sleep, it would take about 7,900 years. Most of these stars are red dwarfs, small, cool stars, much dimmer than the Sun. Red dwarfs have masses between about 0.075 and 0.5 solar masses. Below 0.075 solar masses, an object isn't massive enough to sustain hydrogen fusion in its core, so it becomes a brown dwarf instead of a true star. Red dwarfs make up about 70% to 80% of all stars in the galaxy. They're incredibly common. Yet none of them are visible to the naked eye from Earth. Not one. Even though they're the most common type of star, they're all too dim to see without a telescope. The nearest red dwarf, Proxima Centauri, has an apparent magnitude of about 11. You need a telescope to see it. Barnard's star, the second nearest star to the Sun, is also a red dwarf. It's also invisible to the naked eye. The reason is simple. Red dwarfs are small and cool. A typical red dwarf might have only 10% the Sun's diameter and emit only 0.01% as much light. They're incredibly faint. But they're also incredibly long-lived. Stars burn through their fuel at a rate that depends on their mass. Massive stars burn hot and bright, but die young. Small stars burn cool and dim, but can last for trillions of years. The Sun, a medium-sized star, will last about 10 billion years total. It's currently about 4.6 billion years old, so it's about halfway through its life. A red dwarf with 0.1 solar masses will last about 10 trillion years. 10 trillion years. The universe is currently 13.8 billion years old. 10 trillion years is about 725 times the current age of the universe. The smallest red dwarfs have barely started their lives. They formed billions of years ago and will still be shining trillions of years into the future, long after the Sun has died, long after all the massive stars have exploded, long after star formation has ceased. In the far future, when the universe is dark and cold, and the only light comes from dying embers, red dwarfs will be the last stars shining. At the other end of the spectrum are the massive stars. These are stars with more than 8 times the mass of the Sun. They make up only about 0.1% of all stars. Incredibly rare, but incredibly important. Massive stars are the factories that produce heavy elements. When they die in supernova explosions, they scatter these elements into space, enriching the interstellar medium and providing the raw materials for new stars and planets. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was made inside massive stars and scattered into space when those stars exploded. The brightest stars we see in the night sky are mostly blue giants and supergiants. Rigel, a blue supergiant in the constellation Orion, has about 21 times the mass of the Sun and is about 120,000 times more luminous. It's about 860 light-years away, yet it's one of the brightest stars in the sky. If you placed Rigel where the Sun is, Earth would be vaporized instantly. The surface of Rigel would extend beyond Mercury's orbit. Betelgeuse, a red supergiant also in Orion, has about 20 times the mass of the Sun, but is even larger in diameter. If you replace the Sun with Betelgeuse, its surface would extend past Mars. Earth would be inside the star. These massive stars don't last long. A star like Rigel will only live for about 10 million years. Betelgeuse, already in its death throes, might explode as a supernova any time in the next 100,000 years. When it does, it will briefly shine as bright as the full moon in our sky, visible even during the day. It will be the brightest supernova humans have ever seen. Between the red dwarfs and the blue giants are stars like the Sun. These are called yellow dwarfs or G-type main sequence stars. They make up about 7% of all stars in the galaxy. The Sun is actually slightly larger and more luminous than average for this class. Most G-type stars are a bit smaller and dimmer. Sun-like stars live for about 10 billion years, give or take a few billion depending on their exact mass. They're common enough to be found throughout the galaxy, but rare enough that the nearest Sun-like star, Alpha Centauri A, is about 4.37 light-years away. The galaxy also contains white dwarfs, the cooling remnants of stars like the Sun. When a star like the Sun exhausts its nuclear fuel, it sheds its outer layers and leaves behind a hot, dense core called a white dwarf. White dwarfs are about the size of Earth, but contain about 60% of the Sun's mass. That makes them incredibly dense. A teaspoon of white dwarf material would weigh about 15 tons on Earth. White dwarfs don't generate energy through fusion. They're just hot because of leftover heat from when they were the cores of normal stars. They cool slowly over billions of years, eventually becoming black dwarfs, cold, dark remnants. Although the universe isn't old enough yet for any white dwarf to have cooled completely to a black dwarf, there are also neutron stars, the collapsed cores of massive stars that exploded as supernovae. Neutron stars are about 12 miles across, but contain 1 to 2 solar masses. A teaspoon of neutron star material would weigh about 4 billion tons. That's about the same mass as Mount Everest, compressed into a teaspoon. Neutron stars are so dense that gravity crushes matter into a form that doesn't exist anywhere else in the universe. Protons and electrons are crushed together to form neutrons. The entire star is essentially one giant atomic nucleus. Some neutron stars are pulsars, spinning rapidly and emitting beams of radiation that sweep across space like a lighthouse beam. The fastest known pulsar rotates 716 times per second. 716 rotations per second. The surface of this pulsar is moving at about 24% the speed of light. And there are black holes, the remnants of the most massive stars. When a star, more than about 25 solar masses, explodes as a supernova, the core collapses completely. No force in the universe can stop it. It becomes a black hole. These stellar mass black holes typically have masses between 5 and 50 solar masses. They're much smaller than supermassive black holes like Sagittarius A, but they're scattered throughout the galaxy. Astronomers estimate there might be 10 million to 1 billion stellar mass black holes in the Milky Way. Most of them are invisible, detected only when they're part of a binary system where they pull gas off a companion star. The Milky Way is a complex, dynamic system. Stars are born in nebulae, live for millions or billions of years, and die in various ways depending on their mass. The heavier elements they create are recycled into new generations of stars. The galaxy is constantly changing, constantly evolving, even though the timescales are so long that it appears static to us. The Milky Way isn't alone in space. It's part of a group of galaxies called the Local Group. The Local Group contains about 80 galaxies spread across a region about 10 million light-years in diameter. Most of these galaxies are small dwarf galaxies, containing only millions or billions of stars rather than hundreds of billions. They orbit the larger galaxies, like moons, orbit planets. The Milky Way has dozens of satellite galaxies. The largest are the Large Magellanic Cloud and the Small Magellanic Cloud, both visible from the southern hemisphere as fuzzy patches in the sky. The Large Magellanic Cloud is about 160,000 light-years away and contains about 30 billion stars. The Small Magellanic Cloud is about 200,000 light-years away and contains about 3 billion stars. Other notable satellite galaxies include the Sagittarius Dwarf Elliptical Galaxy, which is actually being torn apart by the Milky Way's gravity. It's currently passing through the Milky Way's disk, leaving streams of stars behind it. Over hundreds of millions of years, it will be completely absorbed into the Milky Way. The Triangulum Galaxy, also called Messier 33, is the third largest galaxy in the local group. It's a spiral galaxy containing about 40 billion stars and is about 3 million light-years away. It may be a satellite of Andromeda, or it may be an independent member of the local group. The largest galaxy in the local group is the Andromeda Galaxy, also called Messier 31. Andromeda is a spiral galaxy, similar to the Milky Way, but somewhat larger. It's about 220,000 light-years in diameter, more than twice the diameter of the Milky Way. It contains about 1 trillion stars, roughly 2 to 4 times as many as the Milky Way, depending on which estimates you use. Andromeda is about 2.5 million light-years away from the Milky Way. That's the closest large galaxy to us. On a clear, dark night, far from city lights, you can see Andromeda with the naked eye. It appears as a faint smudge in the constellation Andromeda. It's the most distant object visible to the naked eye. When you look at Andromeda, you're seeing light that left that galaxy 2.5 million years ago. 2.5 million years. Think about that. The light you're seeing began its journey across space 2.5 million years ago. At that time, modern humans didn't exist. Our species, Homo sapiens, wouldn't evolve for another 2 million years. Our distant ancestors were early members of the genus Homo, creatures called Homo habilis. They were walking upright. They were making primitive stone tools by banging rocks together. But they had no language as we know it. No complex grammar. No abstract thought. No art. No culture in any meaningful sense. They were more like upright apes than humans. And the light you see from Andromeda tonight has been traveling through space since then. Andromeda, like the Milky Way, has a supermassive black hole at its center. This black hole is much larger than Sagittarius A. It contains about 140 million solar masses, about 35 times more massive than the Milky Way's central black hole. Andromeda has been observed and studied for over 1,000 years. Persian astronomer Abd al-Rahman al-Sufi described it in 964 AD, calling it a small cloud. He didn't know what it was, of course. No one did until the 20th century. In the early 1900s, there was a debate about what these fuzzy spiral nebulae were that astronomers could see through their telescopes. Some thought they were clouds of gas within the Milky Way. Others thought they were island universes, separate galaxies far beyond the Milky Way. In 1924, Edwin Hubble settled the debate. He used the 100-inch Hooker telescope at Mount Wilson Observatory to observe Cepheid variable stars in Andromeda. Cepheid variables are stars that pulsate with a period related to their intrinsic brightness. By measuring the period of pulsation, you can determine how bright the star actually is. By comparing that to how bright it appears from Earth, you can calculate how far away it is. Hubble found Cepheids in Andromeda and calculated the distance. About 900,000 light-years. That was the number he published. It's since been revised upward to 2.5 million light-years as our understanding of Cepheid variables improved. But the point stood. Andromeda was far beyond the Milky Way. It was a separate galaxy. The universe was much larger than anyone had imagined. The Milky Way was just one galaxy among many. Hubble's discovery revolutionized our understanding of the cosmos. Andromeda and the Milky Way are approaching each other. Their mutual gravity is pulling them together at about 68 miles per second. That's about 246,000 miles per hour. Fast by human standards, but slow in cosmic terms. At this speed, it will take about 4 billion years for them to collide. 4 billion years from now, Andromeda will fill the night sky. Instead of a small fuzzy patch, it will dominate half the heavens. Its spiral structure will be clearly visible. Individual bright stars will be discernible. And then the galaxies will collide. Not a collision in the sense of stars smashing into each other. Space is too empty for that. The average distance between stars in the Milky Way is about 4 light years. When the galaxies collide, stars will pass through the spaces between other stars. Direct collisions between stars will be incredibly rare. But the galaxy's gravity will scramble the orbits of stars. Stars that were in neat spiral arms will be flung into random orbits. The spiral structure will be destroyed. Gas clouds will collide, triggering bursts of star formation. New stars will be born by the millions, lighting up the merged galaxy with brilliant blue regions of hot young stars. The supermassive black holes at the centers of both galaxies will spiral toward each other. Over hundreds of millions of years, they'll orbit each other, getting closer and closer. Eventually, they'll merge, creating a single black hole containing about 144 million solar masses. The merger will release an enormous amount of energy in the form of gravitational waves, ripples in space-time itself. But by the time this happens, Earth will likely be uninhabitable. The Sun is gradually getting hotter. In about 1 billion years, the Sun will be about 10% more luminous than it is today. This doesn't sound like much, but it's enough to evaporate Earth's oceans. The increased solar radiation will cause more water to evaporate into the atmosphere. Water vapor is a greenhouse gas, so this will cause temperatures to rise further. This creates a runaway greenhouse effect. More heat causes more evaporation, which causes more heat. Eventually, Earth will become like Venus. A scorched world with surface temperatures hot enough to melt lead. In about 5 billion years, the Sun will start running out of hydrogen in its core. It will expand into a red giant, growing to perhaps 100 times its current diameter. Its surface might extend to Earth's orbit. If Earth hasn't been vaporized by the heat, it will be consumed by the expanding Sun. So by the time the Milky Way and Andromeda collide in 4 billion years, Earth will be long gone. Humanity, if it still exists, will have moved to other worlds. Or perhaps will have evolved into something unrecognizable. 4 billion years is a long time. The collision will create a new galaxy. Astronomers call this future galaxy Milkomeda or Milkdromeda. It will be an elliptical galaxy, a smooth ball of stars without the spiral structure of its parent galaxies. Most large elliptical galaxies are thought to form through mergers like this. The collision will take billions of years to complete. The galaxies will pass through each other, swing back, pass through each other again. Each passage will scramble more orbits, trigger more star formation. Eventually, after perhaps 6 or 7 billion years, they'll settle into a single structure, a giant elliptical galaxy containing all the stars from both the Milky Way and Andromeda. About 1.2 trillion stars in total. The Triangulum galaxy will probably be involved too. It may collide with the Milky Way and Andromeda adding its 40 billion stars to the mix. Or it may get flung out into intergalactic space by the gravitational chaos. Computer simulations have modeled this collision in detail. They show the spiral galaxies approaching, developing tidal tails of stars pulled out by gravity. They show the first passage, with stars from each galaxy mingling. They show the galaxies swinging apart, then falling back together for another passage. They show the final merger, the formation of a smooth elliptical galaxy. It's one of the most thoroughly studied events in astronomy. Even though it won't happen for 4 billion years, we understand the basic process very well. The local group is part of a larger structure called the Virgo Supercluster. A supercluster is a collection of galaxy groups and galaxy clusters spread across hundreds of millions of light years. It's one of the largest structures in the universe. The Virgo supercluster contains about 100 galaxy groups and clusters, at least 100. Some estimates put it higher. The exact count depends on where you draw the boundaries, which is somewhat arbitrary because superclusters don't have sharp edges. They fade out gradually into the surrounding void. The largest cluster in the Virgo supercluster is the Virgo cluster, which gives the supercluster its name. The Virgo cluster contains about 1,500 to 2,000 galaxies. 1,500 to 2,000 galaxies, all concentrated in a region about 15 million light-years across. Compare that to the local group, which has about 80 galaxies in 10 million light-years. The Virgo cluster is much denser, much more crowded. In the Virgo cluster, galaxy collisions are common. Galaxies pass close to each other all the time. Tidal forces strip stars away. Smaller galaxies get absorbed by larger ones. It's a violent environment. The Virgo cluster lies about 54 million light-years from the Milky Way. 54 million light-years. When you look at the Virgo cluster through a telescope, you're seeing it as it was 54 million years ago. 54 million years ago. On Earth, it was the early Paleogene period. The dinosaurs had been extinct for about 12 million years. Mammals were diversifying rapidly, filling the ecological niches left vacant by the dinosaurs. The first primates had appeared. The continents were still moving, slowly drifting toward their current positions. India had collided with Asia, creating the Himalayas. The Atlantic Ocean was widening as the Americas drifted away from Europe and Africa. Grasses had evolved and were beginning to spread across the planet, creating the first grasslands. That was 54 million years ago on Earth. And the light we see from the Virgo cluster today left those galaxies back then. The Virgo supercluster is about 110 million light-years in diameter. 110 million light-years. At its center is the Virgo cluster, and the entire supercluster is slowly collapsing toward that center. Everything is falling toward the Virgo cluster, pulled inward by its immense gravitational pull. The Milky Way is moving toward the Virgo cluster at about 250 miles per second. But we'll never reach it. We won't crash into the Virgo cluster because there's a larger structure pulling on us. A structure so large that it contains the Virgo supercluster and several others. In 2014, astronomers announced the discovery of Laniakea. Laniakea is a galactic supercluster, a supercluster of superclusters. It contains the Virgo supercluster, the Hydra Centaurus supercluster, the Centaurus supercluster, the Pavo-Indus supercluster, and several others. It's about 520 million light-years in diameter and contains roughly 100,000 galaxies. 100,000 galaxies. Think about that. The Milky Way is one of 100,000 galaxies in Laniakea. The name Laniakea means immeasurable heaven in Hawaiian. The name was chosen to honor Polynesian navigators who used their knowledge of the heavens to navigate across the Pacific Ocean. The structure was discovered by mapping the motion of galaxies. Astronomers had been measuring galaxy positions for decades. But R. Brent Tully and his colleagues did something different. Instead of just looking at where galaxies are, they looked at where they're going. They measured the velocities of galaxies, determining which direction each galaxy is moving through space. When they plotted this data, they found something remarkable. Galaxies in a huge region of space are all flowing toward a common point, like water flowing downhill toward a drain. That common point is called the Great Attractor. The Great Attractor is a gravitational anomaly in the direction of the constellation Centaurus. It's not a single object. It's a region of space where there's an unusually high concentration of mass. Several large galaxy clusters are located there. The Norma Cluster, the Centaurus Cluster, the Pavo-Indus Supercluster. All of them together create an enormous gravitational pull. The Milky Way, along with tens of thousands of other galaxies, is being pulled toward the Great Attractor at about 373 miles per second. That's more than 1,340,000 miles per hour. We're moving through space at over 1 million miles per hour, pulled by gravity toward a concentration of mass 50 million light-years away. And you can't feel it. You're sitting or standing wherever you are, reading this, completely unaware that you're hurtling through space at 1 million miles per hour. Because everything around you is moving at the same speed. Earth is moving. The sun is moving. The solar system is moving. The Milky Way is moving. The entire local group is moving, all falling toward the Great Attractor. This motion was discovered in the 1970s when astronomers noticed that the cosmic microwave background, the afterglow of the Big Bang, appears slightly brighter in one direction and slightly dimmer in the opposite direction. This happens because we're moving through space. As we move toward one direction, the light from that direction gets blue shifted, making it appear slightly brighter. The light from the opposite direction gets red shifted, making it appear slightly dimmer. By measuring this effect, called the dipole anisotropy, astronomers determined that the local group is moving at about 390 miles per second relative to the cosmic microwave background. Part of this motion is due to the Milky Way's motion within the local group. Part is due to the local group's motion toward the Virgo cluster. And part is due to the Virgo supercluster's motion toward the Great Attractor. All these motions add up. The discovery of Laniakea redefined our understanding of the local universe. Before, we thought the Virgo supercluster was the largest structure we were part of. Now we know we're part of something much larger. Laniakea is just one of many superclusters. Nearby superclusters include the Coma supercluster, the Perseus-Pisces supercluster, the Hydra-Centaurus supercluster, the Shapley supercluster, and others. The Shapley supercluster is particularly interesting. It's one of the largest concentrations of galaxies in the nearby universe. It contains about 7,600 galaxies and has a total mass of about 10 quadrillion solar masses. 10 quadrillion. 10 to the 16 power. A number so large it's hard to comprehend. The Shapley supercluster is about 650 million light-years away. It's so massive that it affects the motion of galaxies across hundreds of millions of light years. Some astronomers believe the Shapley supercluster might be responsible for part of the motion toward the Great Attractor. Its gravity might be pulling not just the Milky Way, but the entire Laniakea supercluster in its direction. These superclusters are arranged in a pattern called the cosmic web. The cosmic web is the large-scale structure of the universe. If you could step back and look at the universe from outside, you would see a pattern that looks like a three-dimensional spider web. Long filaments of galaxies stretch across hundreds of millions of light years. These filaments are the densest parts of the cosmic web, the strands of the web. They contain most of the galaxies. The filaments connect at massive clusters, nodes where thousands of galaxies congregate. These are the intersections of the web, where multiple filaments meet. Between the filaments are voids, vast regions of space containing very few galaxies. These voids are the empty spaces in the web. They're not completely empty. They contain some gas and dark matter. But they contain very few galaxies compared to the filaments. The voids are huge. A typical void might be 100 to 300 million light-years across. Some voids are even larger. The Bootes void, discovered in 1981, is about 330 million light-years in diameter. It contains only about 60 galaxies. For comparison, a typical region of space that size would contain about 10,000 galaxies. The Bootes void is almost empty. When it was first discovered, astronomers called it the Great Void. Some people even called it the Great Nothing. It's one of the largest empty regions of space ever discovered. The cosmic web structure formed in the early universe due to tiny density fluctuations. Right after the Big Bang, space was extremely uniform. But it wasn't perfectly uniform. There were tiny variations in density, quantum fluctuations that got stretched out during the rapid expansion called inflation. These tiny density variations became the seeds for all the structure we see today. Regions that were slightly denser than average had slightly more gravity. They pulled in more matter. Over billions of years, these slight overdensities grew into the galaxies, clusters, and filaments we see today. The voids formed in the regions that were slightly less dense than average. They expanded as matter was pulled out of them and into the denser regions. Computer simulations of structure formation reproduce the cosmic web pattern naturally. You start with a nearly uniform distribution of dark matter and normal matter. You add the tiny density fluctuations from the early universe. You let gravity do its work over billions of years. And you end up with a cosmic web of filaments and voids that looks just like what we observe. The largest known structure in the universe is the Hercules Corona Borealis Great Wall. It's a galactic filament about 10 billion light-years long and several billion light-years wide. 10 billion light-years. Light from one end of this structure takes 10 billion years to reach the other end. That's 72% of the age of the entire universe. The structure is so large that it challenges our understanding of cosmology. According to the cosmological principle, which is a fundamental assumption in modern cosmology, the universe should be roughly uniform at large enough scales. Small scale, you have planets and stars. Medium scale, you have galaxies and galaxy clusters. But at large enough scales, hundreds of millions of light years or more, the universe should look basically the same in all directions. Homogeneous and isotropic. The same everywhere and in all directions. This principle says there shouldn't be structures larger than a few billion light years. Beyond that size, the universe should be smooth and uniform. But the Hercules Corona Borealis Great Wall is 10 billion light-years long, 3 times larger than the theoretical maximum. It exists. We've observed it. We've mapped it. But we don't fully understand how it formed or what it means for our models of the universe. Some astronomers have suggested that maybe our understanding of the cosmological principle needs to be revised. Maybe the universe isn't as uniform at large scales as we thought. Others suggest that the structure might not be a single connected object, but rather a chance alignment of several smaller structures that happen to lie along the same line of sight from Earth. This would make it less significant. Not a single huge structure, but several medium-sized structures that look connected from our perspective. The debate continues. What's clear is that the universe has structure on scales of billions of light years. And that structure tells us something important about how the universe formed and evolved. Every filament, every cluster, every void is a piece of evidence about the early universe, about the tiny quantum fluctuations that existed when the universe was less than a second old, about how those fluctuations grew over billions of years into the cosmic web we see today. The cosmic web is the large-scale structure of the universe. Imagine the universe as a vast, three-dimensional spider web, not a flat web like a spider makes. A three-dimensional foam-like structure extending in all directions. Long filaments of galaxies stretch across hundreds of millions of light years. These filaments are the densest parts of the cosmic web. They contain most of the galaxies in the universe. A typical filament might be a few 100 million light-years long, tens of millions of light-years wide, and contain thousands or even tens of thousands of galaxies. The galaxies aren't evenly distributed along the filament. They cluster together in groups and clusters strung along the filament like beads on a string. The filaments connect at massive galaxy clusters, nodes where thousands of galaxies congregate. These nodes are the densest regions of the cosmic web. The largest galaxy clusters can contain thousands of galaxies all packed into a region a few tens of millions of light-years across. These are like the intersections of a three-dimensional highway system, where multiple routes converge. Between the filaments are voids, vast regions of space containing very few galaxies. Voids are the dominant feature of the universe by volume. They occupy most of space. The galaxies, superclusters, and filaments occupy only a small fraction of the total volume, maybe 10 to 20%. The rest, 80 to 90%, is voids. These voids aren't empty in an absolute sense. They contain gas. They contain dark matter. But they contain very few galaxies. A typical void might contain only a few dozen galaxies scattered across hundreds of millions of light-years. For comparison, a filament of the same size might contain tens of thousands of galaxies. The voids are huge. Typical voids are 100 to 300 million light-years across. The largest known voids are even bigger. The Botez void is about 330 million light-years in diameter. The KBC void, named after the astronomers who discovered it, Keenan, Barger, and Cowie, might be as large as 2 billion light-years across, though this is controversial. If confirmed, it would be one of the largest structures ever discovered. Inside a void, space feels empty in a way that's hard to imagine. If you were floating in the middle of a void, looking in any direction, you would see almost nothing. No nearby galaxies. Maybe a few faint smudges in the distance at the edges of the void, but mostly just darkness. The nearest galaxy might be tens of millions of light years away. It's the ultimate isolation. The cosmic web structure has been mapped in detail through large galaxy surveys. The Sloan Digital Sky Survey, which ran from 2000 to 2008, with extensions continuing to today, mapped the positions and distances of millions of galaxies. When astronomers plotted this data, the cosmic web became visible. They could see the filaments connecting clusters. They could see the voids between them. The pattern was clear and unmistakable. Other surveys have extended this work. The 2-degree field Galaxy Redshift Survey, the 6-degree Field Galaxy Survey, the BOSS Survey, the Baryon Oscillation Spectroscopic Survey, all of them mapping galaxy positions across billions of light years, building up a 3-dimensional map of the cosmic web. The results all show the same thing: filaments and voids. A foam-like structure extending as far as we can see. The largest filaments visible in these surveys stretch across 1 billion light-years or more. The largest voids span hundreds of millions of light-years. And the pattern continues in all directions. Everywhere we look, we see the cosmic web. The Milky Way sits on a filament. The local group is part of that filament. The Virgo supercluster is part of a larger filament. Laniakea is part of an even larger filament. We're embedded in the cosmic web, just like every other galaxy. Our location on a filament rather than in a void is important. If we were in a void, the night sky would look very different. We would see far fewer galaxies. The universe would seem much emptier. Our understanding of cosmology would have developed differently if we lived in a void. We might have thought the universe contained far fewer galaxies than it actually does. We might have thought the universe was younger or smaller than it is. Our location on a filament, where galaxies are common, has shaped our understanding of the universe. The cosmic web tells us something profound about the universe. It tells us that structure exists on all scales. From planets to stars to galaxies to galaxy clusters to superclusters to the cosmic web itself. There's structure everywhere. The universe isn't random. It's organized, shaped by gravity and the initial conditions set down in the first moments after the Big Bang. Now, let's talk about the observable universe. The observable universe is the part of the universe we can theoretically see. It's limited by the speed of light and the age of the universe. Nothing can travel faster than light. Not matter, not information, not anything. This is a fundamental law of physics, one of the core principles of Einstein's theory of special relativity. Light travels at about 186,282 miles per second in a vacuum. Fast, but not infinitely fast. And because light has a finite speed, there's a limit to how far we can see. The universe is about 13.8 billion years old. We know this from multiple lines of evidence. The cosmic microwave background radiation, the afterglow of the Big Bang, tells us the universe's age. The expansion rate of the universe, measured by observing distant galaxies, tells us the universe's age. The ages of the oldest stars, determined by studying their composition and evolution, tell us the universe's age. All these methods converge on the same answer. 13.7 to 13.8 billion years. You might think this means we can see 13.8 billion light-years in every direction. Light has had 13.8 billion years to travel, so we should be able to see objects up to 13.8 billion light-years away. But you'd be wrong. The reason is that the universe has been expanding the whole time. Space itself has been stretching. When we say the universe is expanding, we don't mean galaxies are moving through space away from each other. We mean space itself is expanding. The distance between galaxies is increasing, not because they're moving, but because more space is appearing between them. This is a subtle but important distinction. Einstein's theory of general relativity, published in 1915, predicts that space can stretch or compress. Space isn't a fixed stage where events occur. It's dynamic. It can curve, warp, stretch, and compress in response to matter and energy. In the 1920s, astronomers, including Edwin Hubble, discovered that distant galaxies are moving away from us. The farther away a galaxy is, the faster it's receding. This is called Hubble's law. The recession velocity equals the Hubble constant times the distance. The farther away something is, the faster it's moving away. This was a shocking discovery. It meant the universe is expanding. All of space is stretching, carrying galaxies apart. Now, because of this expansion, a galaxy that emitted light 13 billion years ago has moved much farther away during the time its light was traveling toward us. The light left the galaxy 13 billion years ago. But while that light was traveling through space toward us, space was expanding. The galaxy was moving away from us, carried by the expansion of space. By the time the light reaches us today, the galaxy is much farther away than 13 billion light-years. How much farther? When we do the math, accounting for the expansion of space over 13.8 billion years, we find that the most distant objects we can see are now about 46 billion light-years away. 46 billion light-years. And that's in every direction. So the observable universe is about 93 billion light-years in diameter. 46 billion light-years in one direction, 46 billion in the opposite direction, 93 billion total. That's the distance to the farthest objects whose light has had time to reach us since the beginning of the universe. This creates something called the particle horizon. The particle horizon is the boundary of the observable universe. Beyond it, light hasn't had enough time to reach us yet. No matter how powerful our telescopes, we can't see beyond the particle horizon. Not because the light is too faint, but because it hasn't arrived yet. The light is still traveling through space toward us. Give it another billion years, and it will arrive. But right now, it's still on its way. The particle horizon is constantly expanding. Every second, light from more distant regions reaches us for the first time. The observable universe is getting bigger. Not because the universe is expanding, though it is, but because we can see farther as more time passes. Within this observable universe, 93 billion light-years in diameter, astronomers estimate there are about 2 trillion galaxies. 2 trillion. That's 2 million million. 2 followed by 12 zeros. Each containing anywhere from millions to trillions of stars. The smallest dwarf galaxies might contain only a few million stars. Large spiral galaxies like the Milky Way contain hundreds of billions. Giant elliptical galaxies can contain several trillion. The total number of stars in the observable universe is estimated at around 200 billion trillion. That's 2 times 10 to the 23rd power. 200,000 billion billion. 200 sextillion. If you tried to count them at 1 per second, it would take you about 6 quintillion years. That's 6 billion billion years. About 430,000 times the current age of the universe. If every star were a grain of sand, you would need several Olympic-sized swimming pools to hold them all. Actually, you'd need closer to 10 Olympic-sized swimming pools. Each pool holding about 2.5 million liters, about 660,000 gallons, filled to the brim with sand, and each grain of sand representing a star. A star like the Sun, which could fit over 1 million Earths inside it. And Earth, in this context, becomes incomprehensibly small. The entire planet wouldn't even register. There simply aren't adequate comparisons. But here's the truly mind-bending part. The observable universe is just what we can see. The actual universe is almost certainly much larger. How much larger? We don't know. It might be a few times larger than what we can see. It might be thousands of times larger. It might be infinite. Current observations suggest the universe is flat or very close to flat. In cosmology, flat doesn't mean two-dimensional. It refers to the geometry of space. In a flat universe, parallel lines remain parallel forever. The angles of a triangle add up to exactly 180 degrees, just like in Euclidean geometry. A flat universe extends infinitely in all directions. If the universe is truly flat, then it's infinite. The observable universe, 93 billion light-years in diameter, would be an infinitesimal speck in an infinite cosmos. 0% of infinity. And everything we've talked about so far, every galaxy, every supercluster, every filament of the cosmic web, all of it confined to a tiny bubble that represents essentially nothing compared to the whole. We can't see beyond the observable universe because light from farther away hasn't had time to reach us yet. And we never will see beyond it because the universe is expanding. In fact, the expansion is accelerating. This was discovered in 1998 by 2 independent teams of astronomers studying distant supernovae. They were trying to measure the deceleration of the universe. Everyone expected the expansion to be slowing down due to gravity. Gravity pulls everything together, so it should be slowing down the expansion, like throwing a ball upward and watching gravity slow it down. The question was how fast the expansion was decelerating. Would it slow down enough to eventually stop and reverse, causing the universe to collapse in a big crunch? Or would it slow down, but never quite stop, continuing to expand forever, but at an ever-decreasing rate? The astronomers measured the distances and recession velocities of distant Type Ia supernovae. These supernovae are excellent standard candles because they all have roughly the same intrinsic brightness. By comparing how bright they appear to how bright they actually are, you can calculate how far away they are. By measuring their redshift, the stretching of light due to the expansion of space, you can determine how fast they're receding. The results were shocking. The expansion wasn't slowing down. It was speeding up. Distant galaxies are receding faster than they should be if the expansion were merely coasting. Something is pushing the universe apart. Something with negative pressure that counteracts gravity. Something that makes up about 68% of the universe's total energy content. Astronomers call this something dark energy. Dark energy is one of the biggest mysteries in physics. We don't know what it is. We don't know why it exists. We just know that it's there because we can see its effects. It's pushing the universe apart at an ever-increasing rate. The leading theory is that dark energy is the energy of empty space itself. In quantum mechanics, even empty space isn't truly empty. Virtual particles constantly pop in and out of existence. These quantum fluctuations might create a small amount of energy in every cubic meter of space. This is called vacuum energy, or the cosmological constant. Einstein actually predicted something like this in 1917 when he added the cosmological constant to his equations of general relativity. He added it to make the universe static, to counteract gravity and prevent the universe from collapsing. Then Hubble discovered the universe is expanding, and Einstein reportedly called the cosmological constant his biggest blunder. But it turns out he was right. There is a cosmological constant. It's just not strong enough to make the universe static. It makes the universe accelerate. The problem is that when physicists try to calculate how much vacuum energy there should be based on quantum mechanics, they get an answer that's about 120 orders of magnitude larger than what we observe. 120 orders of magnitude. That's 1, followed by 120 zeros. It's the worst prediction in the history of science. Clearly, we're missing something fundamental about how quantum mechanics and gravity work together. Dark energy has profound implications for the future of the universe. Because the expansion is accelerating, distant galaxies are moving away from us faster and faster. At some distance, currently about 16 billion light-years, galaxies are receding faster than the speed of light. This doesn't violate relativity because the galaxies themselves aren't moving through space faster than light. Space itself is expanding faster than light can travel through it. Light, leaving those galaxies toward us, is like a person on a treadmill walking forward, but the treadmill is moving backward faster than they're walking. They're moving forward relative to the treadmill, but moving backward relative to the ground. Similarly, light from these distant galaxies is traveling toward us, but space is expanding so fast that the light is actually getting farther away from us. It will never reach us. This creates something called the cosmic event horizon. Beyond the cosmic event horizon, about 16 billion light-years away, events happening now will never be visible to us. The light from those events will never reach us because space is expanding too fast. And this horizon is getting closer. As the expansion accelerates, more and more galaxies are being pushed beyond the cosmic event horizon. They're disappearing from our view forever. In about 150 billion years, assuming dark energy remains constant, all galaxies outside our local group will have been pushed beyond the cosmic event horizon. An observer at that time will look out into the night sky and see only the galaxies in the local group. Everything else will be gone, pushed so far away by the expansion of space that their light can never reach us. The observable universe will have shrunk dramatically, not because the universe is smaller, but because we can see less of it. In the far future, trillions of years from now, the universe will be a very different place. Star formation will have ceased as all the gas in galaxies is used up or dispersed. The only light will come from long-lived red dwarf stars and slowly cooling white dwarfs. Eventually, even those will fade. The universe will enter what's called the degenerate era. where the only objects are stellar remnants. White dwarfs, neutron stars, and black holes. No living stars. No galaxies forming or colliding. Just dead embers, slowly cooling in an ever-expanding void. And the expansion will continue. Galaxies will be pushed farther and farther apart. The cosmic web will be stretched thinner and thinner. Eventually, in about 10 to the 100 years, even the black holes will evaporate through a process called Hawking radiation. A supermassive black hole like Sagittarius A will take about 10 to the 100 years to evaporate. That's 1, followed by 100 zeros. This is so far in the future that it's almost meaningless to contemplate. The current age of the universe is about 10 to the 10 years. 10 to the 100 years is 10 to the 90 times longer than the current age of the universe. After the black holes evaporate, the universe will consist of nothing but isolated photons and fundamental particles, spread so thinly that the average distance between particles is larger than the size of the current observable universe. This is called the heat death or big freeze. The universe continues to expand forever, becoming colder and emptier and darker, approaching absolute zero temperature, approaching perfect darkness, approaching infinite dilution. That's the fate of the universe based on current understanding, unless dark energy changes. If dark energy gets stronger over time, the expansion could accelerate even faster. In an extreme scenario called the Big Rip, the expansion could become so violent that it eventually tears apart galaxies, then stars, then planets, then atoms. Everything would be ripped apart by the expanding space. Current observations suggest this isn't happening. Dark energy appears to be constant, but we don't know for sure. We're still trying to understand what dark energy is and how it behaves. Let's talk about dark matter for a moment. Because while dark energy is pushing the universe apart, dark matter is what holds galaxies and galaxy clusters together. Dark matter makes up about 27% of the universe's total energy content. Normal matter, the stuff that makes up stars, planets, and us, accounts for only about 5%. Dark matter doesn't emit, absorb, or reflect light. We can't see it directly. We only know it exists because of its gravitational effects. Galaxies rotate faster than they should based on the visible matter we can see. The outer edges of galaxies are moving so fast that they should be flying apart. But they're not. Something is holding them together. That something is dark matter. Galaxy clusters show the same effect. The visible galaxies don't have enough mass to hold the cluster together. But when we measure the cluster's total gravitational pull, we find much more mass than we can see. That extra mass is dark matter. We've also detected dark matter through gravitational lensing. Massive objects bend space, which bends the path of light passing near them. When we look at distant galaxies through a galaxy cluster, we see the distant galaxies distorted, their light bent by the cluster's gravity. By measuring this distortion, we can map where the mass is. And what we find is that most of the mass isn't where the visible galaxies are. It's spread out in a halo around them. Dark matter. The leading theory is that dark matter is made of particles that don't interact with electromagnetic radiation. They don't absorb or emit light. They only interact through gravity. These hypothetical particles are called WIMPs, weakly interacting massive particles. Physicists have been searching for WIMPs for decades, using incredibly sensitive detectors buried deep underground to shield them from cosmic rays and other interference. So far, they haven't found anything. Other theories suggest dark matter might be made of axions, primordial black holes, or some other exotic form of matter we haven't discovered yet. The point is, we don't know. We know dark matter exists because we can see its gravitational effects, but we don't know what it is. And that means 72% of the universe, the dark matter and dark energy combined, is completely mysterious. We don't know what it's made of or why it behaves the way it does. We only know it's there. Let's step back and think about what we've covered. We started with Earth, a planet about 7,917 miles in diameter. We moved out to the Moon, about a quarter the size of Earth, and about 238,855 miles away. Then to the Sun, which could fit over 1 million Earths inside it, and sits about 93 million miles away. Then to the edge of the solar system, the Oort cloud, about 1 light-year away. Then to Proxima Centauri, the nearest star, 4.24 light-years away. Then to the Milky Way, 100,000 light-years in diameter, containing hundreds of billions of stars. Then to the local group, 10 million light-years across. Then to the Virgo supercluster, 110 million light-years in diameter. Then to Laniakea, 520 million light-years across. Then to the cosmic web of filaments and voids. Then to the Hercules Corona Borealis Great Wall, 10 billion light-years long. Then to the observable universe, 93 billion light-years in diameter, containing 2 trillion galaxies. And finally, to the actual universe, beyond what we can see, which might be infinite. At every step, the scale increased by factors of 10, 100, 1,000, 1,000,000. And at every step, Earth became smaller. Not physically smaller, obviously. Earth is still the same size it's always been, but smaller in significance. Less special, more ordinary. There are galaxies out there that dwarf the Milky Way. IC 1011, a supergiant elliptical galaxy, is about 6 million light-years in diameter, 60 times larger than the Milky Way. It contains about 100 trillion stars. 100 trillion. For context, that's about 400 to 1,000 times more stars than the Milky Way. If you lived on a planet in IC 1011, your night sky would be absolutely packed with stars. The density of stars near the galaxy's center is thousands of times higher than in the Milky Way. You'd see stars in every direction. The nearest star to you might be only 1/10 of a light-year away instead of 4 light-years. Close enough that some stars would appear as tiny disks rather than points of light. The night sky would never be truly dark. The combined light of hundreds of thousands of nearby stars would create a permanent twilight. Constellations would be meaningless because the stars would form an almost continuous glow. And if your planet were near the galactic center, you'd see the supermassive black hole's effects. Gas and dust spiraling inward. Jets of material shooting out from the poles. Bright regions where stars are being torn apart by tidal forces. It would be spectacular, but also dangerous. The radiation levels near a supermassive black hole of that size would be intense. Life might not be possible. IC 1011, formed by consuming other galaxies. It's at the center of the Abell 2029 galaxy cluster, about 1.07 billion light-years from Earth. Over billions of years, it has cannibalized dozens or perhaps hundreds of smaller galaxies. Each collision added more stars, more gas, more mass. The galaxy grew larger and larger. This is how most giant elliptical galaxies form, through mergers. IC 1011 isn't unique. There are many other giant elliptical galaxies out there. IC 1101, about 1 billion light-years away, is roughly the same size. NGC 6,066,000,000 at the center of the Coma cluster is another supergiant elliptical. These galaxies are rare, but not exceptionally rare. Most large galaxy clusters have at least one. The Tadpole Galaxy, officially named UGC 10214, has a tail 280,000 light-years long, nearly 3 times the diameter of the entire Milky Way. Just the tail, not the main body of the galaxy. The tail was created by a collision with another galaxy about 400 million years ago. The gravitational interaction pulled a stream of stars and gas out of the main galaxy, creating a long tail that stretches across space like a cosmic streamer. The tail contains star clusters, regions where the tidal forces compressed gas enough to trigger star formation. These clusters are bright blue, indicating they're young and hot. They're only a few million years old. Eventually, over hundreds of millions of years, the tail will disperse. The stars will drift apart, joining the general population of intergalactic stars. But for now, the tail is a dramatic reminder of the galaxy's violent past. The Antennae galaxies, also known as NGC 4038 and NGC 4039, are 2 spiral galaxies in the process of colliding. They're about 45 million light-years away in the constellation Corvus. The collision began about 1 billion years ago. The galaxies first passed through each other, then swung around, and are now merging. The collision has triggered massive bursts of star formation. Thousands of new star clusters are forming in the regions where the 2 galaxies overlap. These star-forming regions glow brightly in ultraviolet and infrared light. The Hubble Space Telescope has captured stunning images of these regions, showing intricate detail of the star formation process. The collision has also created 2 long tidal tails extending from the main bodies of the galaxies. These tails look like antennae, which is how the galaxies got their name. The tails contain millions of stars pulled out of the galaxies by gravitational forces. This is similar to what will happen when the Milky Way and Andromeda collide billions of years from now. The Antennae galaxies are a preview of our future. These extreme galaxies show us the incredible variety in the universe. Galaxies come in all sizes and shapes, from tiny dwarf galaxies with only a few million stars to giant ellipticals with trillions. From neat, spiral galaxies like the Milky Way to chaotic, irregular galaxies with no clear structure. From isolated galaxies floating alone in voids to dense galaxy clusters where collisions are common. The Milky Way, by comparison, is pretty normal. It's a mid-sized spiral galaxy. Not particularly large, not particularly small. It's not undergoing any major collisions right now. It's not forming stars at an extreme rate. It doesn't have unusual structures like rings or jets. It's just a regular spiral galaxy, rotating slowly, forming a few new stars every year. And that normality is actually fortunate. Extreme galaxies, while fascinating, are often chaotic places. The bursts of star formation that accompany galaxy collisions also produce lots of supernovae. Supernovae release deadly gamma-ray bursts and other high-energy radiation. A nearby supernova could sterilize a planet, destroying the ozone layer and exposing the surface to harmful radiation. The active galactic nuclei, powered by feeding supermassive black holes, can sterilize large regions of their host galaxies with intense radiation. The Milky Way's quiet, steady existence has allowed planetary systems like ours to form and remain stable for billions of years. If we lived in one of those extreme galaxies, Earth might have been sterilized by radiation long ago. Our normality, our averageness, might be exactly what life needs. Let me give you some perspective on how astronomers figured all this out. Because measuring distances in space is incredibly difficult. You can't just stretch a ruler from here to another galaxy. Instead, astronomers use a series of techniques called the cosmic distance ladder. For nearby stars, within a few thousand light-years, they use parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. By measuring this shift, you can calculate the distance. It's the same principle you use when you hold your finger up and look at it with one eye, then the other. Your finger appears to move against the background. For more distant objects, astronomers use standard candles. These are objects whose intrinsic brightness is known. Cepheid variable stars, for example, pulsate with a period that's related to their luminosity. By measuring how bright a Cepheid appears and knowing how bright it actually is, you can calculate its distance. For even greater distances, astronomers use Type Ia supernovae. These are exploded stars that all have roughly the same peak brightness. They're so bright that they can be seen billions of light-years away. The Hubble Space Telescope revolutionized distance measurements by observing Cepheid variables in distant galaxies. Hubble allowed astronomers to measure the distances to galaxies tens of millions of light-years away with unprecedented accuracy. The James Webb Space Telescope, launched in 2021, is pushing these measurements even further. It's observing some of the most distant galaxies ever seen, galaxies that existed when the universe was less than 1 billion years old. These galaxies are so far away that their light has been traveling toward us for over 13 billion years. We're seeing them as they were in the early universe, not long after the first stars began to form. But all these measurements have uncertainties. The distance to Andromeda, for example, is known to be about 2.5 million light-years. But that number has an uncertainty of about 100,000 light-years. For more distant objects, the uncertainties get larger. When we say the observable universe is 93 billion light-years across, that's based on models of how the universe has expanded since the Big Bang. We can't directly measure distances that large. We infer them from other observations. The point is, astronomy is hard. Measuring the vastness of space requires careful work, sophisticated instruments, and mathematical models. And even then, there's uncertainty. But despite these challenges, astronomers have built up a consistent picture of the universe's scale. And that picture shows clearly that the universe is far larger than most people imagine. Some theories in physics go even further. They suggest that our universe might be just one of many in a multiverse. According to eternal inflation theory, the Big Bang wasn't a single event. It's happening constantly, creating bubble universes that spawn more bubble universes. Our universe would be just one bubble in an infinite foam. In some versions of quantum mechanics, every time a quantum event has multiple possible outcomes, the universe splits. All outcomes occur in different branches. This would create an infinite number of parallel universes, one for every possible outcome of every quantum event. These ideas are speculative. We have no way to observe other universes. Testing these theories is extremely difficult, but they arise naturally from well-established physics, which is why many physicists take them seriously. If the multiverse exists, then our entire universe, with its 93 billion light-year diameter and 2 trillion galaxies, is just one universe among infinitely many. And Earth becomes even more vanishingly insignificant than it already is. Let me bring this back to something more tangible. In 1990, the Voyager 1 spacecraft, which had completed its primary mission and was heading out of the solar system, turned its camera back toward Earth and took a photograph. Earth appeared as a tiny, pale blue dot, less than a pixel in size, suspended in a beam of sunlight. This photograph, taken from about 3,700,000,000 miles away, is one of the most profound images ever captured. It shows Earth, as it really is, in the context of space. A tiny speck floating in an enormous void. And that photograph was taken from within our own solar system. Not even from another star, just from the outer reaches of our sun's neighborhood. From Proxima Centauri, Earth would be completely invisible. From the center of the galaxy, the entire solar system would be invisible. From Andromeda, the Milky Way would be a faint smudge. From the edge of the observable universe, the entire local group would be too small to see. Here's what strikes me most about all of this. Every measurement, every calculation, every observation that has expanded our understanding of the universe's size has come from us, from humans. Small creatures on a small planet, confined to one tiny world. We built telescopes and spacecraft. We developed mathematical frameworks. We figured out how to measure distances to objects billions of light years away. We mapped the structure of the universe from the inside, unable to step outside and see the full picture, but able to piece it together from countless observations and calculations. That's remarkable. We're tiny. We're confined to one small world for now. But we're also remarkably capable. We're conscious beings who can understand the universe that created us, who can look up at the night sky and comprehend what we're seeing. The universe is vast, beyond our ability to fully grasp. 93 billion light-years in diameter, 2 trillion galaxies, 200 billion trillion stars, and possibly infinite beyond what we can see. Earth is incomprehensibly small in comparison. If the observable universe were an ocean, Earth wouldn't be a grain of sand on the beach. It would be smaller than a single atom in that grain of sand. Actually, far smaller than that. There's simply no adequate comparison. But Earth is also precious. As far as we know, it's the only place where life exists. The only place where consciousness has arisen. The only place where beings like us can look out at the cosmos and wonder about their place in it. Size isn't everything. What matters is what's here. And what's here is remarkable. Life in all its diversity. Consciousness capable of understanding the universe. All the things that make existence meaningful. Earth might be small, but it's our home. And in a universe that's mostly empty space, mostly cold and dark and hostile to life, a small, warm planet teeming with life is incredibly special. The universe is bigger than you think, bigger than I can adequately explain, bigger than numbers can capture. Because the numbers themselves, 93 billion light-years, 2 trillion galaxies, 200 billion trillion stars, these numbers are so large that they stop meaning anything. Your brain can process the digits, but it can't really comprehend the scale they represent. When I say the observable universe is 93 billion light-years in diameter, you can repeat that number. But you can't truly imagine it. None of us can. And that's okay. You don't need to fully grasp it intuitively to appreciate what it represents. You can appreciate that the universe is vast beyond our ability to fully comprehend. You can appreciate that light from distant galaxies has been traveling for billions of years to reach your eyes. You can appreciate that we live in a tiny corner of an enormous cosmos. There's something profoundly humbling about understanding cosmic scale. It reminds us how small we are in the grand scheme of things. How brief our individual lives are compared to cosmic timescales. How isolated we are in space, separated from even our nearest stellar neighbors by distances that would take thousands of years to cross. It puts our concerns and worries into perspective. The things that seem so important in our daily lives are temporary and local. From a cosmic viewpoint, they mean nothing to the universe. But there's also something empowering about this knowledge. We figured this out. Despite being small creatures on a small planet, we measured these vast distances. We understood our place in the universe. We are tiny, yes, but we're also conscious. We're capable of understanding the universe that created us. And that's something worth celebrating. The universe is bigger than you think. It's bigger than the solar system, bigger than the Milky Way, bigger than the local group, the Virgo Supercluster, or even Laniakea. It's bigger than the observable universe, and possibly infinite beyond that. At every scale we've examined, from Earth to the cosmic web, the pattern is the same. The universe is larger, more complex, and more magnificent than we initially imagined. And every time we think we've grasped its full scale, we discover something new that makes us realize we were still underestimating it. 93 billion light-years, 2 trillion galaxies, 200 billion trillion stars. And that's just what we can see. The actual universe could be far larger, perhaps infinitely larger. In which case, everything I've described tonight is essentially 0% of the total. That's the universe. Bigger than you think. Bigger than anyone thinks. And more amazing than words can properly convey. Thanks for staying with me through this journey across cosmic scales. The universe is vast, and we are small, but we're here. We're conscious. We're looking up at the night sky and trying to understand it all. And somehow, despite our size, despite our limitations, we're succeeding. That's worth remembering. Good night.